All right, thank you, Sam. My name is Peter Sampson. I'm a Program Manager with Sugar Research Australia's Research Funding Unit. Welcome to today's webinar, which is going to be delivered by Professor Andrew Robson from the University of New England. Andrew's presentation is on satellite and ground-based remote sensing for yield and nitrogen mapping in sugarcane. Andrew has 25 years experience of remote sensing. Much of that was with departments of primary industries in Queensland and New South Wales. But a few years ago, he moved to the University of New England, where he established the Applied Agricultural Remote Sensing Centre, which he's the director. The centre is currently working across 14 agricultural industries, but their work in sugarcane is actually the most advanced. So a few housekeeping notices. First, please note that today's meeting is being recorded. It's going to be available on our website. If you're not speaking, could you please leave your microphone on mute to keep background noise down? And if you're having any technology issues, type a message in the chat box, which is on the menu bar on the left of your screen. And Sam Riles from SRA, who's co-host, will make sure everything runs smoothly. Now, at the end of Andrew's presentation, he'll be taking questions, so please take an active part in that. There's two ways you can ask questions. You can either type them into the chat box during the presentation, that's on, up on the left, and I'll ask your questions at the end. If you'd actually like to ask a question verbally, then please use the hands up button on the toolbar, which is next to the three dots, and you'll be invited to ask a question at the end of the presentation. Thank you, and I'll now hand over to Andrew.
Thank you, Peter. Can you see and hear me okay?
Yes.
Oh, that's a good start.
I can't see anything.
You can't see anything?
No slides up yet, Andrew.
No, I had my camera running. I'll change it to share slide now. It's all right. It should be doing. Yeah, can you see my slideshow now?
Not yet, but there might just be a little lag.
That's hilarious. It worked yesterday.
Mm-hmm.
Ah, here we go.
Your light is here.
How are we? Are we seeing it now?
Yes, we are. Thank you.
Excellent. Oh, good morning, all. Sorry.
Just remind everyone to be on mute, please.
Okay. I assume you don't need me. Good morning, all, and thank you, or good afternoon for those overseas that have joined this morning. So I'm going to run through sort of a progression of research over a number of years from the starting work we've done in with remote sensing over sugarcane right to where we're up to now. And that's in terms of yield and nitrogen mapping. So as Peter mentioned, well, we've got a bit of feedback then. Is everybody echoing just now? No, just me? Just me. No?
There is a little bit of feedback.
Can everyone sit there on mute? Yeah. I've just got a bad echo just coming back then. Oh, that's it, that's fixed it. Okay, so I'm now with the University of New England and been lucky enough to set up the Applied Agricultural Remote Sensing Centre. We have 11 staff currently in the centre who are listed there. A lot of this work has been done definitely not just by me, but also Dr. Moshiur Rahman has had a big input into the development of algorithms. And I've also got a list down in the lower section here, if you can see my mouse, of other people who have contributed to this work within our centre. And a couple of them have moved on to other ventures, but their contributions have been greatly appreciated. So I'm going to run through some very basics on what's remote sensing just for those in the crowd who just get them up to speed and then progress through the research results, which are, as mentioned in the sort of lead up, the results we presented, warts and all. So remote sensing is just the measuring of something without physically destroying it. So it's a good way to measure things non-destructively. There are many technologies available for remote sensing, and these are evolving over the years, and they range from satellite to proximal and field-based sensing. The UAV or drone boom that started a number of years ago, tractor-based sensors and airborne sensors, and that's just a snapshot of some of them. When selecting the appropriate remote sensing sensor, there's four main resolutions that should be considered. And that includes temporal, and that's how often the data is available. And a really good example of that is if you're using it for irrigation management, there's no point getting an image or data every month. You need a daily frequency. So that sort of helps determine which ones you choose based on your application. Spectral is the number of, spectral, which is the number of bands, and there's multispectral, hyperspectral. You could also include thermal and in that mix as well. There's the spatial, which is the pixel size and the area covered. So as example, Landsat's closer to your 30 metre by 30 metre pixels, down to your drones, of course, which are your 2 centimetre. So again, depending on your application is what you need. Radiometric is the amount of data sensitivity of the sensor or the information you get. So that comes more into the analytics side of it. So very, very basically how it works, and a lot of people would have seen this in the past. A really healthy plant reflects a lot of near-infrared light, up to 60% of sunlight if it's super healthy. The red, green and blue is how our eyeball sees things. So they're mainly driven by photosynthetic pigments in the leaf and absorption. Red's a really important one, relates to chlorophyll. And as this example shows, as a leaf gets sicker or leaf area index reduces, your near-infrared drops and your red increases. So you have a change in these responses. So it's a very good way to look at general plant health or vegetation health. There is hyperspectral as well, and in recent years, hyperspectral's seen a lot of hype. Basically, hyperspectral is an extension, more wavelengths than multispectral. So here we have the red and the near-infrared, as I mentioned before, but it generally goes up to about 2,500 nanometers, depending on the sensor. It does provide insights into the HONCs, the hydrogen, oxygen, nitrogen, carbon bonds, and those related to protein, lignin, and cellulose, for example, and measures of those and how they change in response to disease, pest, things like that is useful. But I really strongly suggest those using hyperspectral is to try and understand the technology first. What you're measuring through here is significantly affected by other constraints like drought, water. So if the goal is to find a specific wavelength related to a disease or pest, it will get blown out of the water under normal field conditions. So is it the holy grail? No, it's not. It just provides more spectral resolution. So be very careful about tying everything to a specific wavelength in field conditions. I've got a list here of some of the more common satellite satellite providers that we use for the sugarcane industry and a lot of the other research we use. So I won't go through them too heavily, but they range from your very high resolution worldview provided by Maxar now. Has a repeat time of 5 days. It has a 31 by 31 by 31 centimetre resolution for the panchromatic band and 1.24 for the multispectral. It has 8 bands within the near infrared and visible, and another additional 8 bands in the shortwave infrared. This is a really nice research tool. It's really good quality, very high resolution, and we use it quite a lot. And depending on the application, beyond research, it does serve some ground as well. The introduction of Sentinel, 2014, Sentinel-1 and 2016, Sentinel-2, really did provide a massive growth in agricultural applications. The main reason is it's available every 5 days. It's 10-metre resolution for multispectral, and it's free. And that's what it basically comes down to. We do a lot of work on Sentinel for broadacre crops, and a lot of other people do as well. It's a really good resource. And there's some others there. Planet's a really interesting one. It's growing all the time. The microsatellites and their satellite constellations that draw into has availability of 1 to 2 days. 3-metre resolution, so it obviously provides a lot better resolution.
Is now exiting.
Oh, see you, Matt. And also, the commercial structuring of that is done development, and I suggest you talk to those guys directly. Spot we've used a lot for the French-owned Spot or Airbus a lot in the past as well. And Landsat, it's fantastic due to its longevity. Like the constellation's been up since the 70s, and we can access good time series data, which I'll go into. So we've looked at, through the sugarcane, and this is the stuff I'll talk to in this talk, we've looked at yield forecasting in terms of tonnes of cane per hectare from the crop to the national level, nitrogen mapping through a range of different satellite, airborne, handheld and tractor-based sensing, mapping the spatial variability of just crop vigour, looking at impact of natural disasters such as cyclone, Debbie and flooding events, biosecurity threats including YCS, and just general damage, I should say, from cane grubs and soldier flies and rats, for example. But we haven't done this alone. We're lucky to have had a very good collaborative network over the last duration of this research, and they include research agencies, mills, productivity services. There's a lot of growers that have helped us that are not listed here, and as mentioned, other research agencies as well. So we wouldn't be here without their support. We work across the majority through the Life Lease projects. We've worked through most Australian growing regions that extend from New South Wales in the south up to Mulgrave in the north. Very different climatic regions, different growing structures. For example, the New South Wales region stands over a lot of the crop for 2-year cropping, compared to somewhere like the Burdekin, which can achieve up and over 200 tonnes of cane per hectare. So highly variable, highly tropical, high temperatures and rainfall, through to quite temperate and lower rainfall. So some of this stuff will be stating the obvious for a lot of you, but it's worth showing in the context for those who haven't seen it. So right back when we started, 2010, yes, high resolution can identify variability in cane. That's not new. You can clearly see in this image there's high growth areas, and for those that don't know, this is a false colour infrared, so the brighter colours are indicate higher growth. Lower areas of low production as seen here, and you can see this area can be related to many constraints. So this, in this case, was sedicity and salinity. But you can also see things like weeds, cane grub damage, soldier fly damage, and even varieties. So it's all very exciting for those getting into it in the current era of remote sensing, but the ability to see these sort of things is fairly common. NDVI has been used a lot, and a lot of people providing sentinel imagery at the moment are hooked up on NDVI. And as mentioned before, it is a really good basic layer for looking at just variability in any vegetation. Now, NDVI is the ratio of the red and the near infrared, and because the red absorption is quite low, it's a trough compared to sort of other bands or the nitrogen peak, NIR peak and reflectance. It does suffer saturation, and so what we see very regularly in sugarcane is that because it's high biomass and high leaf area, it saturates, which is the saturation of NDVI value, irrespective of the yield produced. And for areas like the Burdekin, this starts occurring as early as 2 or 3 months old. So NDVI is not good for sugarcane. After many years of validation over different indices, we've constantly found GNDVI to be better suited for biomass and yield in sugarcane. And this is substituting the red band for the green. So it's the same ratio, but we use green. Okay, can you actually get a yield out of it, or a yield map or a yield forecast? And the simplest way, and again, this is stating the obvious, is you identify variability in a crop and you use that to select target locations to do sampling. And this is generally a transition of high, medium and low growth areas. You do sub-sampling of in these regions, and in this case, we're cutting 5-metre runs and weighing them in the field. You can develop a nice relationship between GNDVI crop reflectance and tonnes of cane per hectare, achieve a nice relationship, in this case, a linear relationship. You can then substitute that to all the pixels in the image and derive a yield map. So now instead of a GNDVI map, we have a tonnes of cane per hectare, and we can predict average and total yield from all the pixel values. That works really well, and here's just a cluster of examples over those years. So here we have the yield maps, the relationships achieved from those point source measures, and also the accuracies at that block level. So you can see, yeah, they're pretty good, but again, they involve physical sampling. And so for those joining the ag tech run at the moment, have you ever cut cane? Yeah, the perception is it's very easy and very fun and lovely blue days and cups of tea and seeing the wildlife. In reality, it's not fun. It's not fun at all, especially big crops. It's lodged, especially if it's been burnt. It's hard work, and there's no way you'd expect growers to go out there and cut point source samples to calibrate this imagery. So the point source sampling is works, but not a practical solution. So we're very lucky with our work with the sugarcane industry that we have the mill support over the last duration of all the research. The sugarcane industry in Australia is by far advanced than any other industry in terms that they've had every paddock digitised at the mill level for nearly 15 years. This was established mainly through the work of Rob Crosley from Agtrix, who helped them set this up initially. But what it's meant is that we've been very fortunate to have access to boundaries for subsetting imagery quickly, but also the attribute information such as variety, crop age, yield achieved, things like that. So that makes it substantially easier to do the work we've done. So the first sort of step we did to try and remove the point source sampling was take the average of cane blocks, the gene DVI crop average, and then put it against the average yield achieved for a block. And we started, and again, sorry for those who've seen this work before, but I will progress up to where we are now, but it's good to set the context of where we got, how we got to where we are. So in this example, and this is just one of the growing regions, here's a minimal number of blocks from 2008 and 2010. You can see it's an exponential relationship. The spread of data is related to crop age and variety, so that's why we get that spread. In some regions in Australia, we will have 50 varieties. So when we first did this, we thought it was fairly messy. I'm not very happy with R-squared, but amazingly, applying that for an average production. So if we take the average gene DVI for all crops, we substitute it into that exponential equation and predict yield, average yield, we get a strong prediction. And here we have two growing regions over a number of years, and we developed this, and you can see the prediction accuracies are under prediction, 3%, 100% right. These predictions were taken at peak growth stage. So in Australia, that's from end of March to the second week of April. And we developed these for all regions. And so come 2015, we were pretty happy that we solved it all, pack up, go home. That wasn't the case. I'll explain a bit in a minute. So that's the regional forecast, but we wanted to see also, could you use that generic algorithm, regional generic algorithm, to predict at the block level? And here we have the farm, and this is not built on the same data that we've made that figure I showed before. This was a later year. But you can see it's a range of varieties, so 208, Cape 228, 138. And you can see the prediction accuracies, again, taken at that peak growth stage, are quite good. They're acceptable considering it's done by remote sensing and not a yield monitor. So we were quite happy with that. However, there's problems. First of all, there was a lot of concern with the accuracies at the block level. So we were lucky enough to share a number of years of data with a specialised statistician who investigated a number of generalised linear models by adding variety, crop age, area of crop, and different bandwidths into the analysis and see if we could get better predictions by adding those variables or covariates into the analysis. We also had a vet, Everingham, who just left recently, put her skills in climate modelling against 3 of our areas. So it was, could we add climate variability to better predict at the block level? And we did that, or I should say she did that over 3 regions. I won't go heavily into the stats in this. There's reports of all this stuff available. However, what we found is that for the Bundaberg region in particular, that both just the simple exponential value relationship of yield versus gene DVI and additional model of adding different bands as well as area and variety didn't really change the prediction accuracy at the block level, with 75% of the crops, and there would have been about 5,000 within plus or minus of 30 tonnes of cane per hectare. For Condong in New South Wales, they have 2, as I mentioned before, 2 years of growing. The inclusion of different bands only did improve the prediction accuracy by 41%. So we had 50% of the crops within 20 tonnes of cane per hectare. But for the second year, the inclusion of cane variety was required to improve the prediction area by a similar amount, but only 11 tonne cane per hectare. So whilst this was good, and I know there's a lot of machine learning approaches these days where we throw everything into these models to try and develop it, the outcome of this was it's not consistent. It changed for different years, it changed for different regions. So having the additional information is handy, but keep that in mind. The more you overfit or fit a model with all these variables and then try and apply it to other regions, the more likely it'll crash badly. The evaluation of weather parameters was inconclusive, but I very much state there was 5 years of data for this for the 3 regions. So again, climate is rainfall is definitely driving variability in growth, but it's not consistent across regions and seasons. The next issue was that variable growth across each season, as well as cloud preventing imagery at crucial times. And lastly, we did a lot of this with spot imagery, and as it doesn't run in a set orbit, always looking down, such as Landsat and Sentinel, we did have issues with different look angles of capturing the crop reflectance each year. So the examples here I've got of 2 regions, and what each one of these points represent is one crop, the average gene DVI for that crop versus yield over a 6-year period. And for this region, you can see it's really consistent, that the line of best fit, the exponential relationship for all those years is quite consistent, and the spread of the different years is fairly close, and hence why we're getting pretty good predictions. The following one, as you can see, a huge annual separation of data points. And this was a result, I should say, of these different things. So we dug into it a bit further. So we pulled out data for Bundaberg over a number of years. And what we have here is imagery captured over crops over each time through the year, and growth curves for 6 of these growing years. The main point to take away from this is something like 2010 had a fairly flat growth rate from the start of January all the way through to harvest. With these X's indicate where we captured the spot imagery, and for most of them, we did manage to acquire them at the peak growth stage before. So this growth is planting, progression of biomass up to peak growth, senescence, and harvesting. And so when we did manage to get the imagery at the high peak growth, our predictions were quite good. But the one that really showed it was back in 2015, when we got an image quite early and the prediction was really low. We got an image a couple of weeks later, 5 weeks later, and it was spot on. This really showed that our point source capture under the constraints of cloud and look angle was a real issue. So we changed our approach. We started looking at time series modelling, and there had been some work by Molan out of Brazil looking at some data using a time series model. And so inspired by that work and some others that we identified, we investigated in Australia. The benefit is that we had the access to and support of the different mills. So we had really good crop level data for all these regions. So the main way this works for time series is we went back and looked at Landsat imagery over 15 years. And we plotted, so each one of these points represents the average crop growth of a whole region, G and DVI value, versus the time it was captured. And as you can see, you've got a growth curve of basically returning or planting, peak growth, harvesting for each year. Now, one thing that's very distinctly obvious is huge holes in these regions. A lot of Northern Australia is cloud dominated, and therefore it's very difficult to get a Landsat image at the monthly spacing with a monthly temporal frequency. But what was encouraging is that because we had 15 years of data to put against this, we could develop a quadratic equation that fitted all the 15 years in one growth profile. And here we've got an example for Herbert. So you've got to think that each year the growth of these crops is influenced by rain, drought, flood, you name it, pest, everything. But we still were able to establish a good quadratic relationship for each of these growing years. And by looking at what the maximum G and DVI value achieved for each year, we were able to put it against the mill yield achieved and have a secondary equation. So the result of this means that we could get imagery as early as February. We could calculate what the maximum G and DVI achieved for that year would likely be based on historic knowledge. We could then put this into the secondary equation and predict the average tonnes of cane per hectare. And that example there is for Herbert. And here we have some other North Queensland blocks, but we have done it for all growing regions. Again, it's quite amazing the high R squared, or coefficients of determination, achieved for each region, considering again that highly variable growth and the floods and droughts, etc., etc. So as you can see, quite good models for each one. But and I should mention, so some of the growing regions, as I mentioned before, New South Wales has 2 years. So we developed a model for each of the growing years. And again, having access to the mill data, which shows what's 1 year and 2 year crops, when we can segregate the imagery very quickly and apply the different models. This also may be highly relevant to like South American growing regions that do achieve 2 crops in one season. There is the capacity to still build these models within that double growth rate. So does it work? So here we have all the regions and the yield forecasts achieved. So the blue bars indicate the actual average yield achieved by each region. The red one, or the orange one indicates that derived from the Landsat. And the last one is from that single capture achieved at that peak growth stage. And you can see the accuracies are quite good. And you've got to keep in mind that the Landsat forecasts were generally made in February, 4 months before harvesting. So we're really happy with that result. And last year was a really critical test of this approach. We had some of the worst drought conditions that we've ever seen in this country, and in some areas ever seen, way off the charts. But yet we were still able to achieve good forecasting accuracy, even though other methods, commercially used methods, failed miserably. So it really was a good baptism of fire of how this sits in unusual years. So we've automated the whole process now, and that's thanks to a contribution from a number of people here. So all the downloading of Landsat imagery is all automated, the pre-correction, pre-processing, the application of the mill boundaries, the subsetting, the derivation of the application of each regional algorithm, and then the predictions are all automated. So it means we can do it really quickly, and any new regions coming up, we can do it within a day if you've got access to historic data. We've also, Landsat, as I mentioned before, goes over monthly and has the nearly 30-metre resolution. Sentinel is a massive step forward with the 5-day repeat and the 10-metre resolution. So we have transitioned all these time series models from Landsat to Sentinel using, and this is for one of the regions, we have a calibration for every region, which was needed. But also for the single capture spot, we've transitioned that to Sentinel. So now this whole process can all be run off one satellite. So applying it at the, so can you use the time series models to get improved prediction at the block level? So colleague Dr. Moshiur Rahman spent a fair bit of work on this in the last year. So in Australia, we have a 5-month harvesting window, which goes from July to December. So what he did is segregate all the crops based on sowing or return date. And that's easily identified, again, from the mill data that's provided to us, because they have the previous year's harvest date. So that basically sets the first date of return or planting. Now, using that, we segregated that planting date into 2-week bins. So the first 2 weeks of July was bin 1, the second 2 weeks was second half of July, et cetera, all the way up to December. So that's what the bins mean. They're 2 weekly harvesting windows for all the crops. We then looked at that growth rate over a number of years, and as you can see, this is the separation from the planting or return date, but they all hit maximum harvest, maximum growth at that first week of April again. And this reiterated why our single point captures predictions were working quite well around that time. So that was really good refreshing to see that. Sorry, I'm just having a drink of water. And so we looked at applying these models at the different dates. And at the farm level, so these are a cluster of blocks or crops at the farm level. Predictions, again, done early February. And as you can see at the farm level, they're quite good. The prediction accuracies for these ones are quite good. And these indicate the sowing date or the return dates of those blocks on the farm. And at the block level, here we have actual yield predicted from nearly 600 blocks versus predicted. And quite a really good fit again. So we think this is a really good approach for applying for accuracies at the block level. We've developed these models, or Moshiur has developed these models for Bundaberg, and there is the opportunity, if there's interest, to do it for other regions. So providing numbers is one thing. Everyone loves a pretty picture. I mean, that's what sells these days. So we also distribute a number of mapping products that, again, are all automated. So here we have GNDVI classification across a whole region. And the benefits of doing it across a whole region is that for the mills in particular, or productivity services, They get a very good idea of consistently high performing and low performing areas. And that's not just within that growing season, but also over years, how that's changing in response to natural disasters and pest and disease and things like that. The problem with doing it, distributing the classification across all blocks, is that when you go down to the farm level or the block level, some come out as just one value. And whilst that indicates that the grower has very uniform growth in that crop, and also shows them where they're positioned in the scheme of the greater region, it's not so great if they're interested in variable application or targeted nitrogen or something like that. So what we also do is classify every single block into the 8 classes as well. And so what this does is remove the influence of variety in age and visible constraints, such as in this case, it could be a prior drainage line, or it could be a sand lens running through there or something like that. They become quite apparent. And so that's the different products just in the bigger maps. We also generate yield maps at the peak growth stage. And so here we have one of the regions and 4 years of yield map. Oh, sorry, I've got 3 there. And again, you can see the variation or the change in yield. So it's not just a pretty picture, it's actually quantified with yield. And understanding that is useful for many reasons. Also at the farm level, so here we have that same farm over 4 years, and you can see the changing of yield achieved across the different blocks and how the influence of season, age, following different gap crops. So some of these followed peanut and there was huge crop response. So that's really useful. Looking at natural disasters, so in 2017, we had Cyclone Debbie crash through the coastline of Queensland. This area in pink indicates all the sugarcane crops. This is the main path. This is a 50-kilometre swath of the extreme weather conditions, rainfall and wind. This is a lesser extent and less extent. So an image captured after the event clearly showed the influence of the heavy rainfall and heavy wind on this cropping region. Now, we did a pre-cyclone prediction of yield in this region and we got 90.1. We did a post-cyclone prediction and got 71, and it actually came in at 71. So the ability to not only identify the influence of something like a cyclone, but also to quantify the impact on yield is highly beneficial, especially for forward selling and things like that. And it's something that, a climate model, for example, would struggle to compensate for. There was also a flooding event in Herbert in 2018, and working with Wilmar, the Herbert Cane Productivity Services Limited and the local council, were able to look at areas that were influenced by the heavy rainfall and in some case flooding. So again, very useful for quantifying impact. So we have developed the algorithms for each region. We have automated the whole process of subsetting imagery, pre-processing it, applying the algorithms, and disseminating the information. So with the support of Sugar Research Australia, we've just recently got the first prototype out of Sugar Maps, which purely delivers just these maps and forecasts. We're not interested in doing anything else, just that. And it's all built off sentinel imagery with those transitions I mentioned before. So it's currently gone to a number of the mills to assess and a couple of growers to assess, and SRA are looking at options for ongoing distribution. So it's all very simple, very simply to use, privacy login, simple interface for editing data and changing block boundaries. It's highly compatible to the existing mill data, so all their current nomenclature or naming conventions can plug straight in. Distribution of maps, of course, and the distribution of maps in a range of formats. So some people like PDFs, others GeoTIFFs, others as an XYZ ASCII file to go into other machinery, other equipment. Again, this is all we're interested in doing, so we can look at developing APIs to go in specific other people's software who want to do consultancy and stuff like that with that information. The biggest difference between this and all the millions of platforms and free sentinel imagery given at the moment is it has the yield algorithms built into it, which can't be developed without that work over those years. That's yield. Now I'll just go through nitrogen. So we looked at nitrogen response with those different sensors over a number of years, and I won't go through all the trials because there's lots of trials, lots of varieties, lots of crop ages. We were, again, very fortunate to have a good collaborative group that included the University of Queensland, Sugar Research Australia, Farmacist, and obviously ourselves. So here's some examples of some of the trial densities that were run by these different groups. So we investigated WorldView 2 satellite. Again, as I mentioned before, it's got really high resolution for plot size trials and also the multiple bands. We also used field-based spectroscopy, and that was both in the field, looking down at the canopies at certain distance, 50 centimetres above canopy, but also using a leaf clip to stop the influence of light conditions. We also contracted Hyperspectral Airborne Australia to fly hyperspectral imagery over the blocks as well. So we had multispectral, hyperspectral, ground-based. First learning of this is working with the multiple groups, and this is a big learning for everyone else out there. If you're collecting data across a wide range of different groups, ensure you have the same sampling protocol. So what we found is some sample third leaf nitrogen, other ones sample whole canopy. And as you can see, they're chalk and cheese, or apple and orange, or whatever you want to use. They're very different. So if you're building a calibration and you've got data that's totally different, you can't do it. So first thing, standardized sampling techniques. The second thing is the positioning of the trial and the influence of treatments and non-treatment related effects. And here we have the spot imagery captured over this massive trial in false color. Again, that's infrared, showing the bright pink is high crop growth. Here's your GNDVI, and you can see there is a prior stream or drainage line running through this crop that's smashing straight through the bottom of this trial. And when you color code, it always look pretty, but you can see that it is influencing areas of this trial. And you can see it very clearly. Here's all the different plots. This is captured with WorldView, I think, back then. It might have been Iconis. No, it's definitely WorldView, sorry. Again, you see a lot of promotion now saying, you know, remote sensing can see trials and replicates and plots. Yes, it does. That's what it's designed to do. So yes, it's very exciting if you're seeing it for the first time, but it has been done for a long, long time. Here we have that influence of the effect. This is useful for biometrics for people running the trials, because you could actually add the different NDVI responses or GNDVI responses or spectral responses as a covariate in explaining the responses of these treatments and trials. So if you are looking at phenotyping, which is quite big now, it is a very useful covariate. And here we have the influence of that low area on yield and also on leaf nitrogen. So again, imagery is good not only for identifying the response of treatments, but also the non-treatment related responses. Farmacist also ran a lot of strip trials for us, as did University of Queensland Sugar Research Australia staff. And again, you can see them. You know, that's the easy thing. Again, you can see the variation achieved or produced by other effects. So very simply, the results were this: WorldView 2, field spectroscopy, and airborne hyperspectral all identified separation in the low, medium, and high applications of nitrogen at sowing. You can see the separation in quite a number of the spectral band widths in areas. Again, you'll notice the WorldView goes from 350 to 1,050 nanometers, and this is reflectance on this y-axis. The Airborne Research Australia and the hyperspectral go up to 2,500 nanometers. And you can see the later ones add some separation in the later wavelengths. These are the best ratios that were identified over the various trials with the different sensors. So WorldView, airborne hyperspectral, and ASD, the ground-based hyperspectral unit. You can see they're fairly consistent, and they're fairly consistent across trials. And what was supporting, great to see, is that it matched other research. And again, I always encourage people to do literature reviews, see other research, what's been done. You can see that it's quite consistent with prior research. So that was refreshing. And the main thing, it's a red edge based index, and we didn't invent this. It's not new. There's white papers on the use of red edge. And red edge, I'll just go back here, is this transitional point between the near infrared reflectance and red that is really strongly related to foliar nitrogen. So use that one for nitrogen, not NDVI. The downside of this, and this is really worth showing, these are all the trials. So this is your red edge index from WellView versus your nitrogen concentration in percentage. And here you have it in terms of kilograms per hectare. This is the trial year crop stage influence on these fits. So yes, you can get nice fits, but it's all over the place in terms of that relationship. So developing a generic algorithm is very unlikely. This example, this was run in Tally Sugar by Danielle Skojek. This trial was sampled twice, it's 2 years, 2 seasons, and you can see just the seasonal effect. So same person sampling it, same trial, just a year difference, you can see the offset shift. So if you had an algorithm developed from here and you applied it to this year, it's totally wrong. So keep that in mind. The varietal effect, so something like Q183 produced a fairly consistent, strong relationship between foliar and nitrogen and the sensors from the 3 sensors that used to measure it. Something like Q186 poor, and this is related to crop canopy structure, pigment distribution, all sorts of things. And again, demonstrates that a non-varietal specific generic algorithm is very unlikely to be useful. So here, what do you do with it? So one thing is you can possibly develop just a qualitative map that shows variability in red edge. You could take the trial results, the calibrations, and apply them to a whole region to get leaf nitrogen. And this is one from Mackay region and Burdekin. But this is not recommended. We've just shown the influence of variety and season. So at the very least on this case, it's just qualitative that we've used the right index. However, understanding there is influences of variety in years, this could be the distribution of nitrogen. The other one is like doing with the yield, you can get the variability in your red edge band. And look, Sentinel does provide a red edge band in the 20-meter resolution. And if you're only just looking at variability in red edge, you can sharpen it to 10 meters. So you identify your variability again in your high, medium, and low red edge areas. You sample it for leaf nitrogen, such that they do it in rice, and you can build a nitrogen response map. And the chances are this is all going to be a lot more accurate than just trying to do a do a generic algorithm. So you can do that, but again, it requires destructive sampling, which is difficult in cane. So there is a number of software, but with working with Farmacist, they've come up with a way to stack historic imagery, so yield information together. Also EM data surveys, EM 31, 38, soil conductivity, soil sampling and leaf tissue testing together in a composite map over years. And this is an example of a farm done over 10, 20 years, maybe even 20 years. As a result of that, you can identify stable zones of yield and then help that to work out where you can apply nitrogen based on yield potential. And there is some conjecture whether yield potential is the right thing to work with nitrogen. But I suppose if a plant's not going to put on yield or has another constraint occurring, it's not going to take up nitrogen either. So just a comparison, so using the nitrogen rates based on these zones, you can reduce it to 137 units of N for the whole farm compared to our standard, which is that's -60. So nitrogen is important for the Australian industry at the moment because we're under regulation for reef health is in the Great Barrier Reef. So one, reducing the amount of nitrogen to hopefully retain yield potential is a benefit. Secondly, if regulation does come in and growers need to report on how they're applying it, this is a really nice way to do it. Now, I mentioned that need to do point source sampling in the field. We did try active sensors. There's a lot of work done by a fellow called Josh Lofton out of the US using active sensors. And so, again, inspired by some of the work he had done, we trialled, or Farmacist trialled, GreenSeeker, Optirex, NDVI and NDRE, Red Edge Index, and GreenSeeker. It was run over 3 years in 3 regions, multiple trials. The nitrogen rates that were applied were above and below the standard recommended, the 6 Easy Steps method. And the sensors were correlated with measures of biomass, plant population, and crop intake. And this is just a table of all the trials run over the different years. And as you can see, it was quite a comprehensive study and evaluation. So fertiliser were applied is an example of the flow, how it was worked. So fertiliser was applied at the start of the season. Then we had sensing and biomass sampling a number of times through the growing season at different ages, and then again following harvest. Yes, it's easy to get a pretty map. That I can't state that enough. Any of these sensors can give you a pretty map, but whether it is actually useful or tells you the right thing that's where I suppose the science comes in. So yes, the Opterex NDVI was able to provide a nice map of distribution of canopy reflectance in that red edge. So yes, theoretically it relates to nitrogen uptake, and the point source sampling sort of showed that for a number of regions. That's just a contour map. We're smoothing it out to make it potentially more useful for applying it. But these are the results. All the commercial available sensors that we tried couldn't be just plug and played. There was issues with all of them in terms of compatibility, mounting, practicality, communication with tractor software, being able to geolocate where they're doing the sampling to where the nitrogen was being applied. That was all extremely difficult, and there was a lot of work put into that. So keep that in mind, is that don't just buy one off the shelter and plug it on and think it's going to work. The second thing is sugarcane is a big crop. And so there's a lot of research, particularly from people like Mike Bell, that has shown that nitrogen hasn't finished taking up until 6 months of crop age. For areas like the Burdekin in Australia, you can't get on the paddock after the crop's 2 to 3 months old due to its size, so let alone drive a tractor over it. So you're on that quandary of, where do you use this and how do you use this? So I think it's useful if you are looking at using different nitrogen rate formats, whether it's slow release or other, or if you are looking at doing some level of top dressing really early on. The other and the most concerning results is that although you could get a pretty map and although you could get a relationship to nitrogen uptake, it changed from sensor to sensor, from season to season, from variety to variety. So again, it was same as the imagery, it's non-consistent. So you'd have to calibrate it again every year. So one thing that Farmacist did try was just identifying gaps in return crops where due to mechanical damage or other cane hadn't come up. So by turning the sensor, the nitrogen off and on at these gaps did show some reduction of nitrogen, reduced nitrogen application. So in one case, 35% and another in 12.5%. So putting nitrogen where it's potentially not needed. The last couple of slides is just some very quick work on cane grub. Now, cane grubs can cause up to $10 million worth of damage to the industry in Australia. One thing we noticed with cane grub, and this started right back in Markham Valley in Papua New Guinea many years ago, is that this spatial pattern of damage from cane grubs, you end up with cane down, cane up, cane down, cane up. Very different to lodging, soil constraints. So it's a textural response. So we were lucky enough to join forces with the University of Queensland and Dr. Casper Johansson, who is now in Saudi. So he was very proficient in textural analysis through eCognition. So he focused very heavily on spectral and textual analysis to see if he could discriminate cane grub damage from other damage. And as you can see from these three locations, Gordonvale, Home Hill and Mackay, the prediction accuracies of discerning cane grub from other was about 60%, 60% and 67%. Now, whether or not that's high enough to support the use of this, that's up to the respective industries where they are. But what I would say that if you are flying these areas with a helicopter and visually assessing these areas anyway, I would suggest or recommend that you use this approach to also help quantify the damage over large areas. Plus, with a spatial layer such as this, you can use it for targeting insecticide to stop the spread in the following year, or look at the spread or change of these areas over years. And that's something you can't do by just sticking your head out of a helicopter. So I think it would be worth investigating further. So the conclusions, the development of these outcomes have been an evolution of learnings over a fairly long period. The time series approach for yield forecasting presents as a reliable method. It allows forecasts to be made really early in the season. The derivation of regional and block level vigor maps and yield maps, they offer huge benefit, as I mentioned, in terms of variability, pest detection, yield forecasting, forward selling, blah, blah, The transition of Landsat and spot algorithms to Sentinel has greatly improved the ability to obtain cloud-free imagery with the availability every 5 days. The higher spatial resolution is really good, and the costs, you can't argue with that. So really useful. I think the process we've established means it can be transitioned to new satellites as they come on board, as there are many coming on board in the near future. The development of the prototype sugar maps is a very simplistic way to get this information finally out to industry through protected methods and integrated with current systems, and also the ability to plug into other people's agronomic software as well. So remote sensing presents the complementary data layer for improved nitrogen and pest and monitoring. It's definitely not the silver bullet, but it's a very complementary layer that's easily accessible and, as I've shown, quite effective. The last bit is, again, there's a lot of platforms and imagery companies out at the moment. All I'll say is just because it looks pretty doesn't mean it's right. I'd strongly suggest you look at how it matches existing science, ask for accuracies to compare and make sure it's actually doing what it's doing. Because obviously if it doesn't do what it says to do, it damages all the work that not only us, but all around the world have done doing in the space. So I'd like to thank Sugar Research Australia and before that SRDC for funding of this work, Queensland Department of Agriculture and Fisheries and the University of New England. Essential support and collaboration from the mills. We wouldn't have been here without them. Similarly, the growers, the agronomists, and the collaborative research partners. Thank you to everyone. You can access, or they will be available, the 3 final reports that have been put up that demonstrate the progression, that have a lot more information. If you're an academic boffin, as the word was used recently, there are a number of papers that have been developed from not only us, but a number of our collaborators, including CSIRO, James Cook University, as an example. So it goes all the way through the time series, the climate influences, the overlaying with other image layers. So I suggest having a look at those if you're interested. That's it. So thank you all for listening for that long-winded explanation. I think Peter's given the opportunity to now allow you to answer some questions. Thank you very much.
Look, thank you very much, Andrew. Yes, we've got 8 minutes for questions. I do have one question already, which came from Patrick Keeley at Agtrix. Andrew, did your model of nitrogen uptake take into account soil types?
No, it doesn't. It's purely a remote sensing based one. There is always the intention to link it with other input layers, spatial layers, such as soil type. So yes, there's always opportunity to link that.
Okay, I have another question from Patrick at Sydney Uni. I'll just read it off, except it's disappearing off my screen. Were the plots for the yield forecasting were calibrated results? With yield forecasting, it's essential to validate by removing whole seasons of data, building an independent model, and then predicting on the removed year. Is this what was done?
The answer is yes. So both the point source samples of the 5 meters done across 3 years, 4 regions were all cut and weighed. So they were an exact measure of biomass. The consignment data from the mills at the block level is what was used to calibrate the measure of tonnes of cane per hectare. So in the absence in those early years of an accurate yield monitor, that was the only way to get that sort of level of yield data at that level.
Okay. I have a question from Yvette. It's an interesting one. How do researchers access the boundary layer data that's been collected by Agtrix?
Well, ultimately, it belongs to the mills. So I would suggest that's your first point of call. We've been fortunate to have established that relationship with the mills, and we access them under strict confidentiality agreements. They're definitely not commercially available. So I would suggest not bombard the mills, but ask.
Yeah, I mean, a comment from me, the general way to do it is to go to the mill rather than trying to get it from Agtrix, because Agtrix will have some confidentiality arrangements.
That's right.
Another question from someone who I don't know who it is. How how easy would it be to get some of the data to compare the yield estimates year on year? As a soil scientist, I'd be interested to see how the use of your data could be used for digital soil mapping as compared to the use of proximal sensor data.
Well, first of all, the mill data I mentioned is not our data, it's the mills. So we definitely can't disseminate that. It's a mill mill approval process. In terms of the derived layers that don't actually contain, like potentially the forecasted yield maps, maybe, but again, I would seek approval from the mills.
Okay. And I guess a follow-up comment on that from the same person is maybe fusing those layers together will give better spatial prediction of soil properties and identifying zones of soil, water and crop management. So I don't know if you want to comment on that. Perhaps it's done already.
Again, they're all complementary layers. If you focus on a soil layer, there are a lot of other constraints, pest, disease that aren't related to soil. So whilst soil layer is useful, definitely, again, it's just another input. So the more inputs you have, the more chance you can identify what the constraint is and how it influences yield and quality.
Yeah, just those questions were from John Triantafillis, so he may or may not want to follow you up on that, Andrew.
Yeah, no, anyone's welcome to contact me afterwards. That's fine.
Okay, and I'm not sure I've got any other questions.
They're all asleep, are they?
We have a question from Rowan. What are your thoughts on using the recently improved yield monitors on cane harvesters in combination with remote imagery, particularly for VRN application? Also, is there scope to get measures of CCS with these new monitors?
That's a good question. Look, to be honest, I haven't looked at the new commercial yield monitors. We did some work with CSIRO years ago to look at some of the existing ones then, and we found the use of imagery with the yield monitor was a good way to identify potential speed issues with a yield monitor. If they've changed speed, we were able to pick that up, and that was work with Rob Ramley. For the new ones, as I said, I haven't looked at them. Again, if you're using that information for the following season or to understand yield variability over time, then yes, great. But as they're done at harvest, then obviously the information offers limited benefit within that season. Now, the second question was CCS, and again, there's some conjecture about this one. When we did the years of point source sampling, we also measured CCS at all those locations. We also measured soil chemistry and plant chemistry. We found huge variability in CCS within the stalks we sampled at each location and across the farms. And we found no relationship between CCS content and any other parameter. That includes biomass, it includes any soil chemistry. So we could not identify what was driving it. The only loose relationship was the soil boron. And there was a PhD many years ago put out in the subcontinent that did mention that. So my thoughts are that whether or not you can measure CCS on the go is a question, but I think it's going to be so variable. What do you do with it? I don't think you can manage it. So it depends what you want to use it for.
Okay. Thank you, Andrew. And Sam, have I missed any other questions? Because I don't seem to have any at the moment.
Just another one's popped in, Peter.
Where are they popping?
It's in the chat box. It's from Mark Callanan.
Oh, I got it now. Yep. Is the measurement of CCS consistent across the mills?
I will leave that to other people who are working on CCS to comment, but it is highly variable. We did a fair bit of looking at CCS change across a number of mill areas as a result of YCS, yellow canopy syndrome. And that was interesting to look at the spatial variability of YCS across farms, but across seasons as well. So yes, there is variability in terms of how much. Then there's other people working more on CCS. Okay.
Look, we're pretty much at 9:30, so we might wind it up. We've got a number of messages thanking you for your presentation, so thank you for that, Andrew. And I'll also say thank you. For all the people who have participated, I hope you found it useful. SRA is keen to get feedback. Now, in the chat box, there's a link to a few questions. We haven't called it a survey because I know everyone's fed up with surveys. But look, if you could go in there, as I say, it'll only take a minute or two regarding the...
Oops. Lost you.
Okay, so I'll just pick up from there. It's just a very brief survey, just a couple of questions about the research, and we'd appreciate you taking the time to do it. So we'll wrap up now. Thanks everyone for coming along today. And thank you very much to Andrew for presenting. And I will end the meeting now. Thanks so much, everyone.
Thank you all. Bye.